Members of our project is was Hamsi Muhammad Abdullah and Salahuddin Muhammad Sar and Bayur. The supervisor of our project is Dr. Muhammad Adil Arshad Sar. The table contents of our project is background, problem statements, aim and objectives, methodologies and equipments, scope and limitation, survey route, result and discussion, conclusion and recommendation. The background of we are discussed the contents one by one. The background of the project is these are infrastructure pieces that connect two or more distant locations and provide passage for obstacles. Dynamic behavior of highway bridges with basic span traversed by heavy truck can be determined. Smartphone are tiny computers equipped with sensors such as cameras, gyroscopes, GPS, accelerometers, and global positioning systems. They offer powerful processing and user-friendly smartphone apps. Smartphone apps are regarded as the next generation of smart sensors due to their low cost, easy of installation, and ability to store massive amount of data. Problem statements: vibration data collected for different period of time help to determine the current health of the bridge. As of now, there is no such datable record of bridge dynamic characteristics exists. The aim and objectives, first we will discuss aim. The aim overall, the goal of these research is to evaluate the dynamic characteristics of highway bridges. And the objectives devise a strategy to monitor dynamic characteristics, frequencies, and dampings of highway bridges of different planes to determine the relationship between fundamental frequency and highway bridges span length. The equipments we use in our site are the following: smartphone sensors, physical toolbox sensors, and wiring tape. The software apps we are used to project Mute accelerometer, physical toolbox sensor, and processing app MATLAB. Now I would like to invite Mohammed Sar.
So this is our physical toolbox sensor in which we have sent and collected data from bridges. When the truck entered to the bridge, we have started the physical toolbox sensor, and when he excites the bridge and when he left the bridge, we will stop the excitation. And we will stop the and we will collect the data. After that, we will put data can be sent via email, upload Google Drive on Dropbox, and the display chance on Android model can be adjusted from 420 Hz to 5 Hz. The Android mobile model has fixed and model and approximately 2000 Hz. Now this is our MATLAB script in which we have performed and analysis our data. For example, if we take data of one bridge and we analysis on MATLAB to know the frequency, MATLAB to know the time period and to know the Fourier transformations and know the vibration and know the dynamic characteristic. Now change. These are the another one. We have picked only two transcripts. We have a lot of scripts and we will put only two. Now we will talk about scope and limitation. Our scope and limitation of the damping has a big effect on how much and how long bridge has a natural frequency. We are talking about on this fractional frequency and we are talking about a free vibration. We are only interested in free vibration. How bridge move is controlled by the viscous damping model. That is most of the adoptable. It shows how the bridge reacts when a force applied in terms of things like vibration frequency and bridge material. We know how to calculate and how to manage the data and how to show the vibration frequency by the help of sensors, low-cost sensors, by the help of apps and with the help of materials, equipments. That's why we will, this is our scope and limitation. This is our methodology planning. First we should planning for a frequency. After that we will find out the bridge time periods. When we find out with the help of low cost sensors and with the help of accelerometer, then we perform Fourier transformation. Then we will write thesis and defense. On methodology, this is the diagram. I will explain it directly. When the vehicle enter at that place, we will start the accelerometer when the excite. So this is the coefficient of this, and when the exist, this is the slab deformation, and this is the time period, and this is the stress. When the vehicle enters, so he will excite the pressure. When the acceleration data before the truck has entered, and we will keep measuring data after the truck has left, and we will wait for sometimes just for 10 to 15 seconds because the damping is close after that. It will gives the tail of accelerogram. This is our survey route. We start from we will go to Peshawar to Pakistan. We stay at Dashu, and after that we will start from Ochar Nala. This is our route. We work at a lot of bridges, and the finishing point is our Bisham city. This is our study area. We are talking about where we work and where is the route and where are the bridges. We are just talking about this. And the total bridge associated with the study is 12 bridges. And these are the latitude and longitude of bridges from Bisham to Ochar Nala. And these are the peaks. These are the bridges of Jalkot steel bridges, and these are the Khayal RCC bridges. And we are the group when you perform collecting data. And now I am talking about a result of finding a damping ratio, as well as for this we perform a Fourier transformation. Fourier transformation basically converts a time signal to a frequency signal and time domain to a frequency domain. We have a multiple frequency. Fourier transformation give the frequency content in a signal. Frequency with a higher distinct peak. For a higher distinct peak, we will use power spectral density. Now this is the result. When the vehicle enter to the bridge, the result will show the blue lines. And when vehicle left, so the result will show the red lines. And the first one will show the acceleration with the time, and the second one will show the Fourier transformation with frequency, and the third will show the power spectral density with frequencies. Now, this is the explanation of figure from the top acceleration time history. When the blue portion present the force vibration under the moving vehicle load, and the red portion represent free vibration response when the vehicle leave the bridge. And now we will go to the middle. This is the Fourier transformation for free vibration part acceleration data, and check natural and fundamental frequency of bridge. And from the bottom, I am talking about power spectral density of free vibration and part of acceleration, check your natural and the fundamental frequency of the bridges. Now we are talking about the sampling rate. The sampling rate we reduced to from 400 Hertz to 200 Hertz, and we will take a uniform 200 Hertz or 200 sample per second was used for the data. Because there are a lot of rush on the bridge, that's why we will reduce that from 400 to 200 Hertz. Now these are our graphs. So when the vehicle enter and when the vehicle left, this is the Fourier transformation according to frequency, and this is the power spectral density according to frequency. Now we will go to another diagram. This area is the free vibration. This area shows the free vibration. Now when the truck enters and he excites the bridge, so there are a lot of amplitude and frequency. When he left, so he will become like that. The acceleration will become like that, and amplitude will like that, and these powers for PhD will like that. This is the free acceleration, free frequency, free vibration frequency. And go to another. Now this is the another one acceleration which have the time along with the Fourier transformation and with the PhD. When the truck excites the bridge, and this is our results. We will perform this result on software MATLAB. We use that and we use MEMS accelerometer, and we will also use power spectrum. No, not power spectrum, the physical toolbox sensors. We will use, with the help of this, we will find the data. Next. Now I will invite my another friend. He will further explain.
Now we will discuss our conclusion. So now we talk about the results of all of it. So the main conclusion we get from our thesis is when we determine the current fundamental frequency of bridge, we get a relationship between span length and fundamental frequency. That was our one conclusion we make. And the other one, for example, we realize that if someone finds the natural frequency of these bridges after numbers of years, then there is a difference that shows the current health of the bridge as we see in our results. So that's what the second one we discovered. The third one we discovered when we compute the damping as well by noting the time period between two successive peaks. So the results, our result thesis shows us that the road uneven surface can be a source of large forces that change quickly. It's important to remember that both peak damping and bridge damping play a role. So we realize that the most two importance when we were doing our thesis, we realized that the peak damping and bridge damping, they play important role when we are checking the bridge health. So the second one, we realize the maximum dynamic effects on the bridge get bigger as the speed of track goes. Like if the track is going high speed, it will affect more up. So we don't know, but we don't know much about where and how bad and even high bridge roadways are. We doesn't know, but that was our conclusion. And so we make a recommendation. So we can make two recommendations. Our thesis, we realized that the goal is to create a smartphone application. We need smartphone application that can directly interfere bridge frequency by connecting the smart to the bridge railways. If we discover, like if someone sent this discover application, smart application that easily can give us the frequency. But now when we were using our when we visit our field visit, we can easily find the frequency. Because we have to use MATLAB first. We have to enter we have to use sensor, and then we have to do it. So the second one, in our recommendation, when the road surface on a bridge is good, if the road is good, the impact factors of the inside bridges are low for the bridge. This seems to overstate how much of an effect short span bridge has. So the most important thing our thesis was the structural health of the bridge. So we realized that after 2 years, for example, this is an example. After 2 years, the initial damping of that bridge has 5% damping period and natural frequency, and they change. So it means if they change, then the structural health of the bridge will change. So let's say the initial has 0.2. After some years, the initial was 1.5 seconds. After it comes to 1.7. It means the structure has changed. Then we have to do something about it. So what we will do is, when we observe that the damping is the same, if the damping is the same of the bridge, the current is the same or the same conditions before, but the period of the frequency has increased, that will tell us that the bridge has been damaged. So we have to do something about it. Otherwise, it will collapse and it will make damage for our environment. So how can we find time period? We can find time period equals time, total time divided by numbers of peaks. So that's how we can find. And this is our reference.